Good afternoon. So today I want to continue our discussion on recursion. I would like to go over some examples to just drive the point home as to how you've already seen recursion before, give a couple examples of how to utilize it now, and then I want to connect it with your next homework assignment, which is about saying, okay, how do we use the tools that we've created from before, like the file classes, to sort of take new things that we've learned, use them with the old things that we've developed in a way that makes coding really nice and enjoyable, okay, for very high-level thinking activities. So before we get to that, let me start with the code that we developed for the file system, okay, reading from file, writing to file. So I posted that on CCLE in the form of a text file. And really what I want to do is I'd rather put this into header files and CPP files. So let me do that right now, just to kind of emphasize, you know, we started writing these classes for fraction. We had, you know, a bunch of function declarations up top, and we had a bunch of function definitions below main, and we put it in a header file for the code from the class, and then we made a .cpp file which contained a bunch of extra, or just all of the functions. And remember, for all of your functions, you have to, in the definition, you have to write appropriate comments. Okay, so usually I do it, but sometimes I do a little shorthand notation, which is just ... Okay, but yes, this \** indicates to this program called Deoxygen, for example, that this is a special kind of comment, and that this is actually something that it needs to pay attention to when it writes documentation. Okay, so let me just show you guys why we do this. If we look at the fraction class, here is @class fraction @brief stores int over int. Here is points.h. You'll notice point2d has a comments, and color point2d does as well. Let's just okay. So let's run this Deoxygen program, and I think I've already prepped it for this. Yeah. Okay. So I've already prepared it for this for these files. Okay. So when I run, okay, it's going to go through all my files and check for all of the specific commenting styles, and then I click Show HTML Output. And now I've got a fairly well-organized set of documentation. This is an HTML file. You could literally put this on the web. Okay? It's clickable. It's all linked up. If I look at classes, there's my point2d, and there's my comments for it as well. So it says stores XY coordinates as double. If we look at the comments, say stores XY coordinates as double. I have an example there. If I click on point2d, it tells me my the example that I created. That's the code that I wrote. Looks like I need /n. So let me show you just how easy this is to modify. I think I need a /n here, and a /n, and a /n. So then we just rerun it. I'm going to close out. Well, I'll keep it open. Show HTML. We go to classes. We click on point2d. We go to more. And there it is. There's my example created right there. Okay? So it automatically created all this documentation. Here are the member functions, point2d, the default constructor, the constructor with parameters. There's a move, a print, a virtual destructor. It even includes a inheritance diagram. Okay? So we say, oh, okay, color point2d inherits from point2d, and we can click on that, and it takes us to the color point2d class. Okay? Takes a point2d and adds a color. Okay? If we go down here, these are functions that I haven't documented. So if I take a look at, say, this move function for color point2d, if I go to my points, okay, there's my move function. Notice I didn't put any comments in. If I put in comments now saying, you know, moves the point by coordinates say x0, y0. At param, move by x is x0, or the x shift. At param, move by y is y0, or the y shift. Doesn't return anything, so there's not any at returns anywhere. Now if I run deoxygen again, classes, color point 2D. If I go to move, there's my documentation. Okay, moves the point by coordinates x0, y0, parameters. Okay, so this is very important if you are writing hundreds and hundreds of thousands of lines of code, because you will write code which 6 months from now you won't even remember what it does or why you did it the way you did it. Or you might look at it and say, oh, I was stupid back then. I know a better way of doing it now. And then you rewrite it and you mess it up. Okay, so these commenting styles are very important. Another thing, though, is that no, let's just leave it at that. Okay, so like I said, the commenting is very important. I should have another one up here. And remember, \* at file, not fail, file points.h at brief stores the points point 2D, color point 2D, etc. Classes. Give a short description, or maybe a more detailed description of, point 2D class is the base class for a bunch of other classes. Okay, now if I look at currently the documentation, if I look at all my files, I have documentation for fraction.h and fraction.cpp. Now when I redo it after having put in those comments in points.h, now it updates it there. Now where's my points.cpp? So here, wait. Oops, points.cpp. That's what I meant. Okay, there we go. You can fool it too. Let's do it again. Go, click on files. There's my points.cpp, and then it shows up the points.h file without any documentation on it. Okay, so if I go to points.h, probably nothing in this file is well commented. Yeah, there's no comments at the top here. So I can put it up here. I can say at file, points.h, at brief, header file. Okay, I think you get the point. So let's take the code from, oh, my mouse is going phantom on me. Okay, there we go. Let's take the code for file reading and writing, and let's put it into its own file, which we're going to call, I guess, what should we call it? Maybe we'll call it file system, something like that. Okay. So now it's going to automatically try and create a class by this name, but the only reason I went to create a class is because I wanted it to automatically generate the .h and .cpp files for me. I'm going to delete those just like I did with the point2D or the points class. So I do file system. I get rid of this junk here. I go to file system.cpp. I get rid of this, and I'm going to replace it with, excuse me, precisely the code from last time, which is okay. Well, let's take the. We'll take these. We'll get rid of some of these classes. Okay, so we'll take all of the declarations, copy, and we'll put them in here. Okay, and we should definitely add comments to these classes at some point. But let's get rid of. Well, let's get rid of those later. Okay, then we go to file system.cpp, and we take all of this code here. and we put it in like so. Okay. Now we go back to main. And this is pretty much just code I copied and pasted from another text file anyway. So are we going to use this today? Well, maybe. OK. So now if we number include file system.h, square data, multiply defined symbols. This happens a lot, actually. OK, so let's see. Square data. I think we just have to write inline. Yeah, OK. What happens is I declared and defined the function in the header file, which I can do as long as I declare that this function is inline. In other words, the declaration is going to also contain the definition. OK? So I could either write inline, or I can declare, copy and paste into the .cpp file the definition. So here I just wrote inline. And now I have access to my read from file and my write to file, or output to file. What did I call it in the homework? I think I called it write to file or something, right? Yeah. Let's not change it right this moment. OK. So actually, let us change it right this moment. OK, so write to file, and we're just going to copy and paste. There's only a few of these, okay? Just to kind of show you how relatively straightforward it is. And yes, this is what you would literally do. So some programs like Sublime will let you edit all copies of all instance of a particular variable or word or set of characters all at once. So you can say find all instances of output to file, and replace it with write to file, and very quickly it just replaces all of them with one command. So it really, there are a lot of great tools out there to help enhance your programming, and Visual Studio is one of them. OK, so now we can do things like, I don't know, write to file. Let's call it my file. Output. Oh, let's try outputting all the permutations. OK? Let's see. So if I can see out it, let's see. How would I do this? File system, what did I overload it? I overloaded an int and a string. Let's overload, let's print a vector. Of ints. OK? How we're going to do that is we're going to just do a for loop, just like in the code here. So, oh, we want a vector, I guess a vector of strings. OK. Vector of strings. OK. So let's call it oh, no, we just want to be able to output strings. This should work right away. OK, I was misreading the code. Forget about vectors for a moment. Let's just replace cout with output. And I am going to have to get rid of endl. I do apologize for this, but I'll tell you at the end, towards the end of the quarter, you'll see why I have to replace this with /n. OK, look at that. It compiled. All I did was swap out cout with the write to file. OK? Now let's run it. Press any key to continue. Now let's check out. My file. And there we go. Okay? So it's as simple as that. Once you have all the infrastructure in place, then you can do this file reading and writing as if it was the console, and now you have it saved somewhere. You can copy and paste. You can search for, say, the pattern A, B, D, E. Cannot find it. A, B, C. Found it. Found a bunch. OK, so this is the advantage you have when you utilize the existing infrastructure, and the amount of code you need to write in order to do it is pretty minimal. OK? So that's that example there. now we can rerun the deoxygen and regenerate a new source of documentation, but we should really go back at some point and just fully fill in all of those comments. And for your homework, you do need to do that. Okay, any questions on what I did just there with the file, and I put it into the header in CPP, and then I started using it right off the bat? Okay, so let's continue with how to think recursively. And we're just going to go through a couple of examples and set up a framework for how you should break down the solution to a problem into smaller components and how to recombine them. Okay? Ignore that slide. Okay, so let's just recall two very famous functions, which you probably are aware of, but even if you're not, it doesn't really matter. All that matters is the formula that I've written on front right here for you. Okay? You just have to be able to understand what the formula is telling you. So there's the factorial function, and this is the one where the factorial of, say, 10 is just the product of all the smaller integers. Okay? Very simple. Now, you probably thought of it more like a for loop, right? You probably thought of it like, oh, if I was going to compute the factorial of 10, I would probably do a for loop and do 10 times 9 times 8, do like for I equals 2, I less than or equal to n, I plus plus, and then times equals. Okay? But there's also a recursive structure here, which is, well, take out a factor of n, and you multiply by the same function with a strictly smaller input. It's a recursive function. Also, 0 factorial is 1. There are many good reasons for that. You just kind of accept it. 0 factorial is 1. Fibonacci numbers. This is related to, I think, rabbits or something. You guys have probably seen these in some form or another, but basically it's a sequence which adds the two previous numbers in the sequence, and it just starts out with some initial conditions. The initial conditions are actually somewhat arbitrary. You can put whatever you want there, and there are generalizations to the sequence that put in like an A here and a B here, and like for A 5 and B is 7 or something. Like, what is the sequence? Are the properties of the sequence any different? Okay. So here we just choose f of 0 is 0, f of 1 is 1, and then f of 2 is going to be 0 plus 1 is 1, f of 3 is going to be 1 plus 1 is 2, etc., etc. Okay? It's the usual Fibonacci's that you may have seen before. But in particular, this is a recursive function that relies not just on calling the previous or the function on just one smaller input, but on two smaller inputs. Hence why we have two initial conditions. Okay? So now we take a tip from your book on a 4-step procedure for thinking recursively. 1, you think about various ways for simplifying inputs. In other words, how do you get the exact same function with a smaller input? How would you combine what you took out to get that smaller solution, or the smaller problem, with the simpler inputs to a solution of the original problem? In other words, I took something out in order to call the function on smaller inputs. How would I recombine it, assuming that problem was solved? Step 3, those are the main meats of the matter. The main meat of the matter, those 2 steps. But then step 3 is, okay, well, if I have to solve a problem of a smaller input, I have to stop the chain reaction at some point. So I need to specify what happens in these base cases. They're called base cases. Okay? So find solutions to the simplest inputs. That's like your f of 0 is 0, f of 1 is 1. And then step 4 is implement the solution by combining the simple cases and the reduction step. So 4 is just simply saying, just put it all together into one cohesive unit. Call the function again recursively on smaller inputs if that's appropriate, or return the base case values when the inputs get small enough. My version. Oh, this ought to be interesting. Okay, let's see. Find the self-similar structure by taking something away and recognizing a smaller version of the same problem. Step 2, assuming the smaller version of the same problem is already solved, or just assume it's already solved. Step 3, take the solved smaller version and combine it with what was taken out initially to form a complete solution. Step 4, I guess I just took out I took step 2 and turned it into 2 and 3. And I considered the previous step 4 to be obvious. Okay. It's the same thing. So we saw this last time. I don't think this is that helpful to recall again. Let's just look at some examples, okay? So, I guess my examples are based off this idea. The idea is you start with n things, a problem on n things. Don't think of it literally like a sequence. Don't think of it like a numerical sequence anymore. This F means a problem with n things. Like Tower of Hanoi had n disks. F is the Tower of Hanoi puzzle. N is the number of disks. And what did we do? We solved it by saying if we could solve the Tower of Hanoi with one smaller disk, then we can combine those solutions accordingly. Okay? So the idea here is figure out how to separate it out into a smaller version of the problem combined with the stuff we took out to get the smaller version. And then after you iterate, you need to have this base case which says something like when there are, say, one disk, when there's one disk in the Tower of Hanoi, the solution is not recursive. It's just, you just move it. Okay? All right, so let's see some more examples. So step 1, consider various ways for simplifying inputs. In other words, try to conceptualize what's f of n and what's f of n minus 1. Okay? Try to figure out the smaller structure. For example, with string reverse, we started with all of the letters in the word, and in order to get the recursive solution, we took out a letter, and we called the same function on the smaller set of characters. With permutations of the word, we took out a single index from the word, and then we found all of the permutations missing that index, and forget about recombining it. We just, to find all the permutations of the larger word, we take an index out one at a time, and we find the permutations of the smaller set. That's a smaller version of the problem. For the Fibonacci sequence, you just need to know what are the numerical values of f of n minus 1 and f of n minus 2. Similarly with factorial, you just need to know n factorial, you need to know how, if you knew what n minus 1 factorial was, then computing n factorial is simple. Okay. So let's go in reverse of the examples. Okay? So step 2 is combine solutions with simpler inputs to a solution of the original problem, or in other words, assume you have already solved the simpler problem. How would you use that to then get at exactly the larger solution, okay? The larger problem solution. So let's go in reverse. If you knew what the value of n minus 1 factorial was, you would simply multiply by n times that to get the exact answer you're looking for. If you knew the values of f of n minus 1 and f of n minus 2, you would simply add them together in the usual arithmetic fashion. If you had all of the permutations missing, say, the ith letter, you would left append that ith letter to each of the smaller permutations, and that's how you would recombine it. You would do this for each letter as well. And then for the string reverse, if you had the solution to the reverse of these letters, you would right append the letter R that you took out initially. Okay? So again, you assume the smaller version of the problem is solved. You assume the smaller version of the problem is solved. You assume you know the smaller values input, and you just map out exactly how you would recombine them to get the larger solution. Step 3 is find solutions to the simplest inputs. In other words, 1 factorial is 1 or 0 factorial is 1. For Fibonacci sequence, f of 0 is 0, f of 1 is 1. Okay? That's going to stop the chain reaction. For permutations, all permutations of no letters is just the vector consisting of the single string with no characters in it. Or permutations with a single letter, that is the vector consisting of a single string object with the letter A in it. Okay? With string reverse, again, same thing. String reverse, the empty string should return the empty string, or string reverse on a single character should return a string object with that exact same character. Finally, step 4, implement the solution by combining the simple cases and the reduction step. Okay? So for factorial, we need the function set up so that factorial of n is going to be equal to n times factorial of n minus 1. But we need to check to say if n is equal to 1, don't call this again, just return a 1. Or if n is equal to 0, return a 1. Similarly with Fibonacci. Fibonacci of n is the sum of Fibonacci of n minus 1 and Fibonacci of n minus 2, as long as n is larger than, that's a typo, n is larger than 2. Let me just change that right now. Okay. Okay. Similarly, with, let's do the permutations, we took out each index, found all of the permutations on the smaller set of characters, combined it in, but then when that smaller set of characters was empty, or just a single character, we returned basically a vector consisting of a single string, which was no characters in it. Okay. And then for string reverse, it's the exact same thing, which is and this is literally the code you would write. You write add to the reverse of those letters, and you check to see first if the input word has size, which is 0 or 1, you just return what was input. So here's an example which specifically outlines the different cases. So let's see. Check for base case, else recurse. Okay, so if word.size is bigger than 1, so if you have a word consisting of at least 2 characters or more, then apply the recursion step, which is take the substring consisting of exactly 1 character starting at index 0, append it to the reversal of the string with starting the smaller strings consisting of all of the characters starting at index 1 to the end. So that's a strictly smaller string. So you're going to keep calling reverse string over and over again until you get to the condition, which is word.size is equal to 1, in which case you'll just return the word. So this will return the word. It'll write append here. And then it will return that larger word. That'll exit out of its function call, combine with the character you took out there, et cetera, et cetera, et cetera. Okay. Fibonacci is similar. Fibonacci, numerical sequences are actually really easy. That's your homework gives you like 4 or 5 numerical sequences. You just take the formula and you can almost literally write it verbatim. There's really not much more to it. Okay? The hard part, what makes the assignment challenging, is just putting in the infrastructure for writing to a file and just setting up the recursive functions and the base cases. And once you've got that all figured out, there's really not any math you need to understand or know. It's literally just formula here. I copy more or less the exact same way it's worded math-wise into C++, and it all just magically works. Okay? So same thing here. If n is 0 or 1, return n, right? So f of 0 is 0, f of 1 is 1, so you just return the input. If it's negative, just return 0. Just pick some value for it. Yes, you do need to consider these cases. Yes, these are the most important cases to consider, especially in an interview. If you ever go for a coding interview, they're looking to know that you've covered all possible cases. They also want to know that you've covered what happens when n is, say, int max. Did you handle that case correctly? When does this function resort to numerical overflow? Okay? So you can write a function like this just fine, and in like 5 minutes, or not 5 minutes. You write a function like this right away. Okay? But then if you're not aware of all the possible things that could go wrong, the debugging aspect of this function could take you days, weeks, months, etc. Okay? So you have to have a keen awareness of for which values of n could be input and what are the possible values of n for which things could go wrong. I don't emphasize it as much when I teach because I figure this is something that you can do. These are detail-oriented things, and I'm just trying to give you all the big picture tools initially. Okay? But it's definitely something that you should be aware of, and if you want to dive deeper in that, you can ask in office hours, and we can go through some of the more tedious aspects of programming, especially numerically. But otherwise, you're just literally copying the formula, and instead of f, you're writing Fibonacci, and that's it. Okay? It's exactly as if you were just doing math, okay, or just writing a mathematical formula. Factorial is the same. If n is less than or equal to 1, return 1. Here, I'm really not doing a good job, okay? Because if n is negative, actually this should return some type of error. I think it's either a domain error or range error, to be more technical, but it really should cause an error if n is strictly negative. Okay? But then otherwise, you just call the function on a smaller input, multiply by n. That's literally the value that you want. Okay, but now let me just put the brakes on for a moment. Okay. This is one of the things that when I was a PhD student, my advisor really emphasized with me, and he gave me this lesson over and over again, which was we started thinking along a certain path. We did a bunch of little things. We worked out some various aspects of a problem, and then at some point, invariably, you come to a conclusion, and you say, oh, cool, that's an interesting conclusion. But you have to stop when that moment happens and just think and ask yourself, does this conclusion make sense with all the other body of knowledge that I've accumulated up to this point in time? Okay? So here's where it applies here. Don't just use a new tool because it's new or savvy or someone told you that you should always do it this way. Okay? You probably would not want to use recursion to calculate the factorial function. Okay? It's actually much more efficient to do it in the form of a loop. Okay? Same thing with Fibonacci. Okay? For Fibonacci, the recursive solution is actually the absolute worst thing you could possibly try and do. Okay? Yes, we will actually come up with a convincing argument which demonstrates why you would never implement Fibonacci in the recursive fashion. That's coming up in the next section. Okay? So just because you have this new tool does not mean you always have to use it. Okay? Sometimes it's a fantastic use of resources, sometimes it's actually not. So here's an example with Fibonacci. If you call Fibonacci on the number 7, really all you need are 7 values, right? You start with f of 0, f of 1, you get f of 2, you just save that, you get f of 3. All you really need to do is to save those current 2, add in the next one, and just kind of piggyback, or I guess leapfrog is the term, right? Until you get up to 7. But if you do the recursive version, f of 7 calls f of 6 and f of 5. What does f of 6 call? 5 and 4. What does f of 5 call? 4 and 3. Okay, so rather than just calling or calculating, say, 7 arithmetic operations, we've really exploded with the number of function calls and arithmetic. We're really you all know what I'm trying to say, okay? We're unnecessarily reduplicating calculations which have been done before, okay? So this is why at some point you stop and you think and you say, okay, what am I actually doing here, and is this the best thing for me to be doing? Okay? So the solution is always to think, okay? Don't just compute, but so on the other hand, this is what the non-recursive Fibonacci might look like. Would you rather read this code or the recursive code? Probably the recursive code, right? The recursive code is much simpler to follow and understand. This code right here, I mean, I wouldn't want to look at this. If something goes wrong here, it would take me quite a bit of time to actually work through all the details of, okay, what's assigning what to what and when and how should that be fold or fold 2? Which one of those goes there? Okay, so there's a trade-off. Sometimes, most of the time, the recursive solution is the most elegant and simple to implement to read and to understand. But in cases like this is actually much, much more efficient than the recursive solution. Okay? So those are the choices you have to weigh. You have to weigh, for example, all right, I know the recursive version is bad, but is it really that much worse than having to look at and decipher code like this? Okay? The answer is actually, yeah, you would much rather look at code than this than work with Fibonacci recursively. But you won't know that until later. Okay, so also in the same idea as recursion is this idea of a helper function. So for example, when you actually implement, so consider the following function called isPalindrome. Do you guys know what a palindrome is? A palindrome is a word that is spelled the same forwards as it is backwards. Okay, so you call reverse string on this word, and you couldn't have told that it was, you couldn't tell if it was reversed or not. Okay, it's spelled exactly the same front and back. If you get rid of all those punctuations, a man, a plan, a canal, Panama is in fact a palindrome. It's kind of cool. So the question is how would you test to see if a string is a palindrome? How would you test to see if a string is a palindrome? Someone give me a very simple but possibly inefficient solution. Yeah. Okay, that was the simple, inefficient answer I was looking for, which is take the word, call reverse string on it, check to see if they're the same word. Okay? So again, we found a solution. Now what if and then the reason why he actually hinted at a better solution, but the reason why I wanted to start with this solution was so that we could think about this and say, wait a minute, what if the word is 1 billion characters long and the first characters and last characters are not equal to each other? Then it doesn't make any sense to do the remaining operations of reversing the entire string and comparing it. Okay? So we found a solution that just doesn't scale very well. Okay? Now, the simpler thing to do, of course, is to... Yeah, so you look at the first and the last one, like you said initially, okay? And you compare those. And now if those don't match, what do you know? Not a palindrome, you can just stop right now. Return false. If these do match, then what do you need to do? Move to the next two. Or, rather than thinking in terms of pointers, what if you deleted the first character, deleted the last character, and then did what? Call the function again on the smaller word. Okay. Light bulb. All right. Now, it's probably more efficient to just move the pointers one by one. Okay? Calling a function actually does involve some overhead. But the idea is still solid. The idea is actually not a bad idea. Okay? So, in this case, you may want to create a function called isPalindrome, and rather than actually calling it again and again and creating a new word, what you might want to do instead is take a hybrid of those two approaches. So you still want to pass in the exact same word. You don't want to make a copy of this word, but you also want to pass in the values of the current indices. Okay? So what you do is you say, okay, well, check to see if this word is a palindrome by checking if this word with these two indices match. And if those letters match, corresponding to those two indices, then increment the one on the left, decrement the one on the right, and call the same function again until they either meet or crisscross. So you don't want to just call the isPalindrome function with a bunch of starting indices and ending indices. You just want a single is palindrome function, you input a string, and it does the stuff for you. So what you're going to create is what's called a helper function. In other words, it's going to be a function that it gets called inside of the larger function. So you have the isPalindrome function. It accepts a constring reference. And rather than have the isPalindrome function be, the 3-parameter version, you just create the 3-parameter version. And, all isPalindrome does is start the chain by calling the function with the starting index and the last index. And then this function isPalindrome, the 3-parameter version of it, actually does the work of checking if the two characters match, and then calling itself, not the general isPalindrome function, but it calls itself again. Oh, do I not? I guess I have code posted on. Do I have it here? It may be. No, it's in the next one. We look at code 10. Let's do the most recent one. Oh, maybe that's too slick. Okay. There's my isPalindrome function right here. Okay. So there's both versions of it. The implementation is down here. There it is right here. So it checks if the indices crisscrossed. And if they did, it returns true, because if it got this far and the indices crisscrossed, everything checked out up until that point. Otherwise, it checks the two characters at those specified indices, and if they match, then it calls the function again by incrementing the two. The leftmost one goes incremented up, the rightmost one gets incremented down. Otherwise, it just returns false. Okay? So this isPalindrome function with 3 parameters is called the helper function. Okay. The final thing about recursion that I'll say, we're not going to really use this, I don't think, at all, but it's the same idea, but it might come up at some point where you say, wait a minute, I've got 3 different functions, for example, and f of n, well, at each stage it does call a different problem with smaller parameters, but it's this other function. And g of n maybe does something similar as well, but it definitely calls something with a smaller function. And you have everything basically going in a downward direction. Okay? Then it's fine. It works out. Okay? As long as all the paths eventually end in a base case, you're fine. Okay? So the mutual part is the sense that you're not strictly doing f of n and f of n minus 1. You're doing f of n and g of n minus 1, but g of n calls something either of the same level of a different function or of a smaller of a same one. Okay, so all the paths eventually lead to smaller inputs for which you can apply the base case. Okay, so, but the idea is very simple. We've been using size t. I guess when I first taught the course and threw this in there, there's a really nice article that I read at first, and it basically it summarizes what I've been saying from the beginning of the quarter. So there's just a link to that article there. Okay, so let's take, well, for example, let's take the Fibonacci sequence, right? Okay, so how would we love to be able to write code? Write to file, say Fibonacci sequence. Do I want the sequence or just a number? Just do the Fibonacci number. Well, I'll just say Fibonacci, okay? Something like this. And then we can do Fibonacci of, say, 10. Oh, again, I can't do endl. I have to do /n. Okay. I run the code. I go to my files. There's Fibonacci. Oh, oops. Let's call it .txt. Run it. Fibonacci.txt. That's f of 10. Fibonacci of 10. Okay? So that's how easy your homework assignment should be. All right? If you can get it to work out right. You have various recursive functions you need to implement for the next week's assignment, and it should be as simple as creating a write-to-file object, and then just in a for loop, as you would normally print out a sequence to the console, you can just print it to a file. So let's say do that. Let's say for I equals, say 0, int I equals 0, I less than, let's say 20, I plus plus. Call Fibonacci of I. We'll load up the file. And there are all the Fibonacci numbers. Okay. The other thing is these numbers grow quite rapidly, as do a lot of the sequences in your homework. So you can't really go beyond. Let's just see what happens if we try to do like 50. Well, first of all, it's going to take a lot longer than we thought, because I'm using the recursive version. Oh, this actually is going to take a lot longer than I thought. Okay, we're going to borrow the what is this? This is f? Okay, we're going to borrow the function f from the code. Okay, here's f. This is going to be the non-recursive version of Fibonacci. And you'll see there is a very noticeable difference between the recursive and non-recursive versions. So here, for small values of the input parameters, the recursive one and the non-recursive one are going to be about the same. But as you saw, for n equals 50, the Fibonacci, the recursive one, actually took a noticeable amount of time, whereas right now, okay, we ignore the output, but it was like that. Now if we go to the file, oh, why does it go away each time? Okay. Okay, so there's a bunch of, okay. Now all of a sudden they turned negative. Is there any reason why they should turn negative? Yeah, it's not because somehow magically you adding two positive numbers gives you a negative number. It's because you've exceeded the amount of space in the size of an int. Okay, so this number, whatever comes after 18363111903, that number is larger than int max, or in other words, the largest possible int variable that can be stored. Okay, so you got to be on the lookout for things like this. You can implement the functions, you can run the code, but again, these are the little errors that come in, and that these are nothing. No compiler complained. There was no runtime error. All that required, all that we have to go off of is thinking, as if to say, okay, this is what was supposed to happen. This is what did happen. Does this make sense of what was supposed to happen? And if it didn't, if this thing showed up, you have to ask yourself why. And if you don't know why, you got to find out. Okay? But the idea for the homework assignment is look, is if you don't implement these classes which handle the file reading and writing for you, it's going to be a lot more difficult. If you do use them, it's effortless. Okay? And that's the main lesson that I'm trying to instill for 10B. Which is in 10A, you just try and learn how the things fit together and how they work and how, what is an if statement, what is a for loop. In 10B, we're converging towards this idea of not just how do you do it, but how do you do it in the right way, not the right way, but how do you do it in a way that makes the coding process much easier and high level so you don't have to do a lot more sort of deeper level thinking. Okay? So that's that, and when we come back on Friday, I guess we'll move on to the sorting and searching part of the course.